Alright, so this video is going to look at the amines topic from the A2 chemistry specification. It might be quite a long video. It's going to pretty much run through the entirety of the amines topic. So I'm going to start off with, well, what is an amine, going through to a bit about naming them, looking at how we can make amines in a couple of different ways, and then looking at their base properties, and then finally ending on a bit about aromatic amines, just as an aside, really, to sort of fit in with the whole thing really of amines, and it kind of comes up obviously there because we are talking about the amino group. So first of all, what is an amine? Well, as I just said, this term amino group, it's something really that has this NH2 part to it, and that's the easiest way to think of it. When we look at the naming, it's not always true that it has the NH2, but it's based around this sort of molecule here with an alkyl group ideally attached here. In terms of the A2 specification, that's what you're going to get, an amino group here. So it's something that contains this group. This would be the functional group of the amine. Amines, like alcohols and things like carbocations, can be put into they can be classified. They go into classes, and what I mean by that is they can be primary, they can be secondary, and they can be tertiary. They can be quaternary, but I'm going to leave that for now and just stick with primary, secondary, and tertiary. And just with any other of the times when you've seen primary, secondary, and tertiary is in the class of amine or class of alcohol, it's to do with really how many alkyl groups are attached. So primary, one alkyl group. And so if you don't know this shorthand here, primary 1 degree, 2 degree, 3 degree, primary, secondary, tertiary. Secondary here, 2 alkyl groups. Tertiary, 3 alkyl groups, and obviously you can guess then quaternary would be 4, but as I say, I'll look more at that and how that can happen in a bit. So I think the first thing we'd do would be to look at actually a couple of examples, really looking at the idea of primary, secondary, and tertiary, ignoring quaternary, and actually how we would name these amines, because depending on what class we've got, it really depends on how we name them, but it's actually reasonably straightforward. So I'll just put that back up there. Also known as the amino group in some instances. So start with the primary amine. Nice simple one. Stick a CH3 group on there. That would be named as methyl amine. If anyone's seen Breaking Bad, it's methylamine. That is the methylamine they talk about, just say it in a slightly different way. So methylamine, here we go. So it's named as per the methyl group that is attached to this amine spine, if you like, this amine sort of backbone, methyl group attached. If that was an ethyl group, C2H5, it'd be ethyl amine, etc. Propylamine, butyl, pentyl, hexyl, whatever, doesn't really matter. Secondary amine. So we'll go for, I'll give you a couple of examples here. We'll do one that looks like this, and I'll do another that's a little different. So first one, 2 methyl groups. Just with any organic chemistry, we would name that therefore as dimethyl amine. In terms of its structural formula, I'll write this out here actually. This one would be CH3 NH2. This one we could write as CH3 2 NH, because we've only got the one H now, don't NH2, that's incorrect. Over here we would have a different one, and this would be ethyl methyl amine. So following the usual rules of naming, and it's going alphabetically. So ethyl methyl because it's E and then M amine. Again, a secondary amine because we have the 2 alkyl groups attached. Finally, move this down a little bit, a tertiary, just through ease really. I'll draw 3 methyl groups, and as you can probably guess, trimethyl amine. So there we go, that's how we name them. The name always has this amine on the end, And what we do is we only change, we name what's attached to the amine group. We'll just put these on here. And over here we've got ethyl methyl amine, C2H5, CH3, NH. Okay, so a bit about naming there. Next thing I'm going to look at then is going on to think about how can we make an amine, so the production of amines. Now actually, if you can remember back to AS, and this is obviously A2 now, if you can remember back to AS, you will hopefully remember nucleophilic substitution. And within that, you used a nucleophile of ammonia, and that made you an amine. And the easy example was something like, we could use something like bromoethane. So we could say we've got C, Br, stick all our bonds in, all the rest here, and then we've got our ammonia molecule with its lone pair going into there. That's going to move on to there. Our intermediate then is going to be the like that, and then finally we're going to have, we'll choose this one, going there onto the nitrogen, with potentially something coming and stealing this hydrogen away, but I'll ignore that. So this is how we make an amine. We start with a haloalkane, and I've just here made, my end result would be ethyl amine. It would be C2H5 NH, like that. So I would have produced ethyl amine. Now, those of you who are reasonably astute will at this point think, well, I've got ethyl amine. That's a primary amine. But actually that in itself has a lone pair of electrons on the nitrogen. Now there's nothing to stop that reacting with the bromoethane. And it can do. You can find that the bromoethane can actually be reacted with the amine, as I'll draw out in a second, to produce you another amine. At this point I will say that if you are looking to produce just the primary, just the primary amine, use excess ammonia. That helps to prevent this kind of reaction going on and just lets this one occur, therefore producing as primary amine. That's something that is occasionally asked in exams. How would you make the primary amine? You know, conditions required, so it'd be ammonia in excess, so potentially 2 marks there, and that has come up in a recent paper I've looked at. So what I'm going to do is I'm going to rub out these various parts and just change this diagram to fit in with what I want it to, really, and the new nucleophile that's going to attack. So if you want to jot anything down, by all means do, and I'm just going to keep adding to it, and hopefully it won't be too confusing. So I can keep this bit there all the same, that's not going to change, and I will just rub this off for now, just out of ease really, so I can not get confused where I am. So we had ethyl amine. Now what we're saying then is this time our ethyl amine can come in and it can attack our initial haloalkane, and in doing so obviously we can get a further reaction. Now I'm just going to abbreviate this just to make it a little bit easier and clearer so it doesn't take up too much room. So here we go, ethyl amine, again same attack as before, boom, carbon, off it goes. Now we end up with that attached, C2H5 group. Now you can see we have diethyl amine, which of course is a secondary amine, and that's not actually true at the minute, apologise for that. Once this reaction has occurred and we've lost that here, we will end up with diethyl amine. once this hydrogen has basically been lost. We end up with the ethyl group, ethyl group, ethyl group with nitrogen and one hydrogen. So C2H5 2 NH. That would be our product in this case, the secondary amine. But of course, this thing here still has a lone pair of electrons, and so it can attack again. You hopefully can see where this is going to end up going, so I'll rub this out and look at it again and see where we can go to now. So I'll rub this bit out. We had diethyl amine, so I could have actually kept that other bit. There we go. Exactly the same. The diethyl amine comes in, boom. That goes across, and here we end up with a nitrogen joined, a hydrogen, C2H5, and a C2H5. And we will get the same thing happening across mechanism because we have our positive there, don't forget that. The end result here being triethyl amine, which is a tertiary amine. But of course, the end result, when it happens, and I'll just edit this, supposed to do another one, will still have a lone pair of electrons, and you guessed it, it will go in and it will react again. Could have kept them there, but there we are. And now we have the triethylamine attacking, and here we go. C2H5, C2H5, C2H5. Now what you've made here is actually the final step, and this is the quaternary structure that you can form. We now have an amine that has 4 ethyl groups, so it's tetraethyl amine in this case. And what you find with these sort of things is that actually these are quite useful in certain areas, which I'll come on to in a second. With all of these reactions, what you can produce is also obviously the as intermediate. So if I go back to, for example, the I'll go back to the start actually, the ammonia, back to the beginning. So ignore this, it does not equals this at the minute. What you would produce down here is you would produce the amine, but you would also produce ammonium bromide. You would produce an ammonium salt there. So it's actually another sort of tetra ion. I guess here that tetra ammonium, or the ammonium ion as it is. And the reason we get the NH4 plus formed, if I just start this again, is because when we have our bromoalkane, in this case the bromoethane, the next one, which was what I drew at the very beginning, when I actually have this positive intermediate, then what I will find is that I said about this arrow happens there, we have the electrons moving, and I said actually you have something else that comes in. Well, in the initial stages, that's actually ammonia that comes in, and it takes that, and that's where we get this NH4 coming in. Br minus is coming from there. This is giving us the NH4 plus, which is just another point worth sort of remembering, that you can get that in each step. Obviously you are ejecting that, and you can produce various different salts depending on whether the ammonia comes in here, or whether, I don't know, whether another load of secondary amine came in, primary amine, tertiary amine. You've got to base it on the question, see what it's asking you, but it's really having an awareness that the product, the primary amine, the secondary and the tertiary amine are all nucleophiles, which can take the place of the ammonia in the nucleophilic substitution reaction to produce the next class up. Obviously ending with the the ammonium, or the quaternary amine. The reason we stop there is because at that point there we have no more lone pairs, so it isn't acting as a nucleophile anymore, which means it obviously can't go through with any more reaction. So I'm just going to put these bits just back in that I had to start with when I initially had my amine coming in, my triethyl amine coming in to make my tetraethyl amine here. And I mentioned that these have these quaternary amines. And what you can find is that actually in conditioners, so conditioner for hair, also fabric conditioners, what they do is they basically, when you wash your hair, you wash your clothes, put the fabric conditioner in, what happens is the surfactant, which is essentially a quaternary amine, but what we would find is, and I'll just get rid of this because I don't want it to start becoming confusing, thinking I'm making all these things. What you'll find is that rather than have just these fairly short hydrocarbon chains attached to this here, you would have a long hydrocarbon, and this there would be this is your what's classed as a cationic surfactant. And if you look on the back of shampoos and all the rest, you will see various ammonium amine based things, and they are actually the cationic surfactants, particularly conditioners where you have ingredients on the back. So as I said, hair and fabric conditioners, and the way they work is really, this is attracted to the hair, this thing here, it's attracted, forms a layer, and actually it just ends up, it helps us to reduce the buildup of static electricity. So particularly in hair, less static electricity is going to give you less frizziness and all the rest, which is obviously a bonus to people who use conditioner. That's why they use it. They want nice, luscious hair that is all shiny and sort of lays flat, not all fly away and all the rest of it. So that's a use of the quaternary amine that's formed. Okay, next thing I want to look at is another way to actually make amines, and that's via the reduction of nitriles. Now this again actually links into the AS, because nitriles again can be made from the cyanide ion, potassium cyanide, or you can use hydrogen cyanide, although it's very dangerous, so we tend to not use that. So the cyanide ion nucleophile substitution, we make a nitrile, and a nitrile, for example, could be something like propane nitrile. So CH3, CH2, N, if we get it right, that would help, CN. And what's happening here is this is a C triple bonded to an N. So this would be propane nitrile, a nitrile, denoted by the carbon nitrogen group that it has in it. The cyano group makes it the nitrile. Now this can be reduced, and this can be reduced to form me an amine. In this case, I would produce propyl amine, or propylamine as people in America might say. Now obviously this isn't going to balance, I can't just turn that into that, so I've got to do a bit of tweaking. I've got to make it look a little bit more respectable in what I obviously add to it, and you have to do this using a reducing agent. So just to get rid of this to tidy things up slightly, we've got to use a reducing agent. Now we can, in terms of an equation, we can generalize that and we can say plus 4H in a square bracket, and this here, if you've never seen it before, it just means reducing agent, the same as O would be an oxidizing agent, but obviously in this case we're not using that, we're just using the H here in a square bracket. So H in a square bracket reacts to form as our propyl amine. Now you're not required to know anything in terms of, for this particular one, you're not required to actually have any mechanism. There is a mechanism that you will come across which involves the use of the H minus as a reducing agent, but that isn't this one. So you are not required to do mechanisms here. You're just required to do conditions and reactants. So what can we use as the reducing agent? Well, you've got two options. Number one, LiAlH4, lithium tetrahydroaluminate. Now you might say, oh well, that looks a bit like NaBH4, sodium tetrahydroborate. Yeah, it's quite similar, but this is not strong enough to reduce the nitrile, so we have to use something stronger. This is the lithium tetrahydroaluminate. Now the next mark, and this is in a recent paper, the next mark is to say in ether. Okay, so don't worry really too much about what that means. It's just what's being used as the solvent here. So it's lithium tetrahydroaluminate, LiAlH4 in ether. That will get you 2 lovely marks. Other option is we can reduce using hydrogen. And what this is, it's a slightly more easy one to sort of remember. And if you kind of look at it, it makes sense. If we add hydrogen in, we can kind of see that we are going to basically just add the hydrogen in here, which is what we want. To use that, it's a catalyst is required, so we can use H2 with a nickel catalyst. In terms of reaction for that, you can actually write it out a little bit different. You don't have to use this generic sort of H here as the reducing agent. The reaction's a little bit more sort of straightforward. Just remember what it was we were reacting to start with. Go into my propyl amine. Balancing it up, we stick 2 there, which obviously takes up for the 2 hydrogens need to slot in there, and the 2 hydrogens need to slot in there. So that's another way then of making the amine. We can reduce a nitrile. Okay, 2 methods. We use lithium tetrahydroaluminate, or we can use hydrogen also to turn it into the amine. 2 options. Basically, you just got to learn these and be able to put them on just onto paper if required. Okay, almost there now. Going to look at amines as bases. So, amines as bases. And we're talking about, when we say bases, what I mean here is I'm talking about proton accepting. So they are proton acceptors. They are fitting the Bronsted-Lowry definition of a base, a proton acceptor. And there's 2 on the specification. There's 3 that you're required to look at. The first being the primary amine. Second being ammonia, and the third being an aromatic amine. So if you haven't done aromatic stuff just yet, it's basically a benzene ring attached. So to draw out these, we would find ammonia. Draw out like this for ease. We've got the primary amine, so I'll pick, we'll have methyl amine. And for the aromatic amine, we'll just have an ordinary phenyl amine. Something like that. There we go. Now there's one important thing we need to include on this, and this is the lone pair on each one of these. And this is actually, it's the lone pair which changes the ability of the amines to act as bases. And what we find is that good base, bad base. And it's going on a scale across to there. So ammonia, okay base. Primary amine, better base. Aromatic amine, worse base. And there's reasons as to why this is the case. It's easier to think of this, to look at this one and this one as the reasoning ones, and this is just in the middle. That's fine. What you do need to make sure you mention of this is there's a key word to use. Okay, if you do not mention this in an exam, you're just going to lose marks. It's often underlined in mark scheme, which means you've got to have it there. And that term is availability. You must talk about the availability, and that is the availability of the lone pair. And what I really mean by that is the more available the lone pair is, the more easily it will accept a proton. It will bond to a proton, therefore acting as a better base. So here we have a more available lone pair. Here we have a less available lone pair. Here we have a medium lone pair. It's like Goldilocks, medium lone pair. Reasoning for that. Starting over here then. So the reason for our lone pair being very available. Well, you may remember it's mentioned within the AS in the alcohols topic, something called the inductive effect. Now the inductive effect is the ability of an alcohol group to really push electrons onto the thing it's attached to. So in this case, my methyl group, my alkyl group here, can push electrons toward the nitrogen. And what that does is it essentially, kind of maybe quite simplistically, is that even a word? Simply just the word. Quite simply, it sort of pushes these lone pairs further out, which means it's easier for something else to come in and bond to them. They are less closely attached to this. They are more available. They are more available to be protonate, or for protonation to take place, so a proton to an H plus to join on. So key thing here then is inductive effect. Pushes electrons, lone pair, more available. And that would work fine as an answer. So good base, we like that. What we don't like is this one over here, and the reason is kind of the opposite thing happens. If you've looked at benzene and how it works, you'll see that this circle is looking at this idea of delocalized electrons, a ring of delocalized electrons which exist in this, what is a 6-carbon skeleton, I guess, with hydrogens attached to it as well. The electrons exist in this weird sort of ring here, and what we find in this case is the complete opposite here. This is much less available, and what happens is these electrons sort of become involved with these delocalized electrons here, and what that means is that these electrons are now much less available. And there's a phrase you really need to use, and they're less available because the lone pair has become delocalized onto the benzene ring, or you could say partially delocalized, but the idea of it's become delocalized and is joining in with the ring. The reason I'm specifying that is in a recent past paper that I was looking at, this question was basically comparing, I think, a primary amine and an aromatic amine, and it was perhaps methyl amine and perhaps phenyl amine, but what it wanted was, it specifically was looking for the term availability. That was underlined in the mark scheme. It had to be introduced, and also it was looking for this idea of these being delocalized. That was really, really pushed, and they wanted you to have that. So there you go. Inductive effect, more available, mediumly available, much less available. Great base, okay base, terrible base. That is the reasoning for it. There you go. Okay. Final point. Amines, going to look at aromatic compounds that involve sort of various reactions that will allow us to produce an aromatic amine. So what I'm ultimately going to be producing is, I'm looking to produce, as was on the previous part there, I'm looking to produce phenyl amine. Phenyl amine. Phenylamine, maybe, if you were, again, maybe an American person. And to write that out, that would be C6H5NH2. This being the C6H6 normally, but we've lost a hydrogen here, and we've got the NH2 group joined on. Now, how can we what can we start with to create a phenylamine? Well, we can start with nitrobenzene. This guy here, nitrobenzene, and again C6H5, this time NO2. And what I can do is I can reduce this. I can reduce it, so I'll use my generic reduction, and I'll get a couple of waters on the other side as well. So I'm reducing my nitrobenzene to an aromatic amine. Now, as with everything else, there are conditions required for this. Our condition is going to be tin as a catalyst, and we're going to use concentrated hydrochloric acid for the reaction, and we're also going to do it under reflux, which at this point you should know what reflux is. If you don't, you need to look it up very, very quickly. That was part of the AS. As another point to note really on this, This reaction has an intermediate, and the intermediate is a phenyl ammonium salt. And the way that we do that is the way that we form the phenylamine from that is our phenyl ammonium salt. We essentially react the phenyl ammonium salt with sodium hydroxide, and that essentially removes one of the H pluses, which is making it into the ammonium salt, and allows us to produce the phenylamine. So this is the intermediate step here. React with, get the phenyl ammonium, react with sodium hydroxide, and we produce the phenylamine. Now I realise that's been gone through the whole thing fairly rapidly, but I think I've covered pretty much all the bases there. Again, if there's anything anyone's got issues with or questions, please do put them in comments, or message me or whatever. But there you go. Amines. I hope that's been of some help.